My name is Caleb Harris, and the purpose of the Falling Motion Lab was to compare real-world falling motion to two computational models, one including only gravity and one including gravity and drag. My real-world model was dropping a lacrosse ball across a dorm floor. The gravitation-only computational model represents only gravity acting on the ball. This model is unrealistic, as there are other forces acting on falling objects. The other model represents realistic falling motion, since it includes gravity and drag. The equations to represent these models are the impulse equation and the position update equation. The main physics principles are Newton's second law of motion. The momentum equation, mass times change in velocity, equals F net delta t, is tied directly to the kinematic equation, V is equal to V naught plus acceleration times time. Vf is the final velocity in meters per second, while V naught is the initial velocity, also in meters per second. A represents acceleration in meters per second squared, and t represents time in seconds. The system is a lacrosse ball, and the surroundings are everything else in the universe. The initial velocity is 0 in the x dimension, 0 in the y dimension, and 0 in the z dimension. The initial position of the ball is 0 meters in the x dimension, and 0.004662 meters in the y dimension is 0 meters in the z dimensions. The code for the gravity-only model was simple. I edited the mass initial conditions to fit my object. Then I used the momentum principle to get the velocity. This velocity was used in the position update to find the position. The drag model was the same except for I included the proportionality constant, the square of the speed, and the force acting in the direction to opposed gravity. The computational models were used to represent drag and the lack of drag. There is net force in both models, so the ball's velocity changes. The main difference is that one model only includes the gravitational force, while the other includes gravity and drag. In the y dimension, the drag acts in the positive y direction, while gravity works in the negative y direction. This observation relates to Newton's second law of motion, which states when a net force acts on an object, the object will accelerate in the direction of the net force. Possible sources of error are the incorrect values of my proportionality constant. Finding this value was very tedious, and I think it's really impacted my data. Also, I did not properly edit my video in Tracker. There are too many frames that include me holding the lacrosse ball. The model with drag represents terminal velocity because the net force has to be 0 in terminal velocity. Terminal velocity is the maximum velocity of a falling object in which the net force is 0 from gravity and drag canceling each other out. The terminal velocities will be the same no matter if the object was thrown versus dropped. As seen in my graphs, the velocities have the same general behavior. However, the thrown objects will reach terminal velocity sooner.